last lesson, we looked at average velocity, and we saw that to find that, you had to make a chord going from one point to another and just look at the average gradient along that chord. Today, we're looking at instantaneous velocity and acceleration. So it's important to understand that when we have a function for displacement, which is how far we are from the x-axis, or velocity or acceleration, to get from one of these to the next, all we need to do is to differentiate it with respect to time. Now, we're dealing with motion and rates, so it makes sense that instead of differentiating y with respect to x, we're differentiating x, where x is our position relative to the origin, and we're differentiating with respect to time, where time is often measured in seconds. Now, this makes sense because a rate needs to be with respect to time to see how it's changing as we go along. So velocity really explains the change in displacement, and acceleration explains the change in velocity. So some notations that we need to be familiar with. Displacement is x, so we'll have x equals, and it will be in terms of t. Velocity, unsurprisingly enough, can be expressed as dx dt, which makes sense. You're differentiating displacement with respect to the time. You're seeing how the displacement changes over time. And that same notation is repeated here when we find the second derivative. Acceleration then would be d squared x over dt squared. So we're seeing how the velocity has changed with respect to time. Now, velocity also has its own letter v, and v standing for velocity. That makes a lot of sense. At the same time, acceleration has a, where a stands for the a in acceleration. We need to be careful with that one because we've got other a's that we use for constants and things in other formulas. We also have another notation whereby putting a one dot above the x or two dots above the x shows that it's the first derivative of x or the second derivative of x. Now, neither of these are really very descriptive because they don't explain what you've differentiated with respect to, whereas these two really show that you're differentiating with respect to time, which to me is a little bit more informative. The v is nice and easy, velocity. Now, we've got one more here that we haven't talked about. If acceleration is the differentiation of velocity with respect to time, it makes sense that if you've started with some displacement formula in terms of x, you've got the second derivative here. But also if you've started with a formula for the velocity and you've called it v equals something, and this will also be in terms of t, then it makes sense that if you differentiate velocity with respect to time, you could give it this notation, dv dt. So then for acceleration, we have all these notations that mean the exact same thing. So we need to be familiar with spotting these in our questions. And then the units are quite straightforward. We have displacement in meters, and then we have velocity in meters per second. And then if we're seeing how velocity's changed over time, then that is meters per second per second. Now, don't forget that meters per second can be written like this. And if I have meters per second, this is a fraction over a fraction. And we know that when we have a fraction divided by something else, that's the same thing as multiplying and flipping, you can see that you end up with the seconds squared on the bottom. So it can be written this way, meters per second squared. It can also be written as meters seconds to the minus 2. So you might like to write that one down as well, because these are units that we can use or we can spot in our questions.